Welcome to this M1 video on connected particles. Now, basically, if you have a system involving motion of more than one particle, the particles may be considered separately. However, if all parts of the system are moving in the same straight line, then you can also treat the whole system like as a single particle. So for example, if you have a car pulling a trailer, you'll basically have the car is on a horizontal track, you have the tow bar, and then you have the trailer. So obviously these two have two weights. The car will have a force driving it forwards. There may be resistances coming back off the car and off the trailer. There'll be tension in the tow bar. And you can treat this as kind of one overall particle where you combine both the weights into one and you basically treat it as if it is just that one particle. So if this was, I don't know, 1,200 kilograms and 2,000 kilograms, then this would be like 3,200 kilograms, and you'd have your total force forwards, F here, and then like say your resistance 1 and resistance 2, and this will be the combined resistance. Okay, so you have, and obviously these have normal reactions, should call it R, but anyway. So that is kind of what we're looking at, but equally you can treat them as separately. Like I can just look at the trailer, for example, and the forward force then would be T, the tension in that tow bar. So I have to kind of assess when I've got a problem, whether I should treat them all as one or whether I should treat it as just part of the system. So like just the trailer or just the truck, the car, whatever it may be, a train, carriages, and so on. But I think truck and trailer is like a kind of pretty standard question for these types of things. Now, other than that, there's nothing new to this. It's just about setting it out properly with a diagram. Okay, so you can see what's happening and then solving the problems using what we already know. So let's jump into the first example. So here we have two particles, P and Q, of mass 10 and 6 kilograms respectively. They're connected by a light inextendable string. Particle P is pulled by a horizontal force of magnitude 80 newtons along a rough horizontal plane. Particle P experiences a frictional force of 20 newtons and Q 12 newtons. So the first thing I want to do is a diagram. Okay, so let's look at what's happening. So I'm just going to put them as rectangles. The particles, you can put them as circles as well. But let's put them as, for now, rectangles. They are connected like so. So the front one is 10 kilograms. So that's 10 G newtons down, and the back one 6 kilograms, so 6 G newtons. Okay, and this is obviously P, this is Q, and this has a reaction force. I'll call it RP, and this one RQ. You could call them R1 and R2 as well. So P is being pulled by a horizontal force of 80 newtons. Now there's tension in this string, and that's how we represent the tension. The tension is kind of in both directions, okay, because this is pulling back, so this would feel a tension going this way, whereas then because this is pulling it along, the string experiences a tension in this direction. So that's why we have the two arrows pointing towards each other. Now they also have frictional forces, so I'll put these on in red. So this one has a frictional force of 20 and this one has a frictional force of 12. Okay, so that is what I've got all together, and we are accelerating to the right. So find the acceleration of the particles. So whole system, you don't need to write that, but we're resolving then horizontally to the right. So we've got 80 newtons minus 20 minus 12, okay, equals, so just let me rub that out a second. What I'm doing is F equals ma. So the force is 80 minus 20 minus 12. The total mass is 16, and A is the acceleration. So it's as if I'm dealing with this as one item. You know, I could, for example, have redrawn it. You know, that's 16G, that's 80 newtons, that's 32 newtons, and that's R. So that's what I could have drawn just as a single particle. Okay, so that is, you know, kind of what I am doing. So 80 minus 20 minus 12 is 48. Divide by 16. A equals 3 meters per second squared. Now, part B. Find the tension in the string. So to find the tension in the string, I must either consider particle P or particle Q. So if I consider particle P, and again we resolve horizontally. So that is now using F equals ma. We've got 80 units going forward minus T minus 20. Okay, so I'm just considering this 80 forward and there's T and 20 going backwards. And then that is 10 kilograms and A is 3. Okay, so that's what I've got. So 60 minus T equals 30. T is equal to 30 newtons. But just to show you, I could have used Q. So for Q, actually I'll do this in red. Okay, it would have been using F equals ma, T going forwards, and just 12 going backwards equals 6 times A. So T equals, so that's 18 plus 12, which is 30 newtons, the exact same answer. Okay, so I could use Q as well, but you know, it's just as easy to use P. Now, part C, let's pop this over here. Now, part C, I'll explain how the assumption about the string have been used. So there's two assumptions: inextensible. So what does that mean? That means that the acceleration of the mass is the same. Because it doesn't extend in any way. Okay, there's no kind of like, you imagine if it was like something that was elasticated, they would accelerate at different rates because one would pull, the elastic would stretch, and then as the elastic contracts, then the other one would then speed up quicker. So, you know, that type of thing doesn't happen. These are fixed as if it's just like a rod holding them together, so they accelerate exactly the same. Okay, and then the other one that we were told was light. Right, so this now, the tension is constant or the same throughout the string. Okay, and then also being light means mass of string is, oh, what's the word? Oh, negligible. Okay, so we don't have to consider the mass of the string. Okay, so that's the, you know, this example. Now let's have a look at another example. Now, before we get into this example, Newton's third law of motion states that for every action there is an equal and opposite reaction. Okay, what that means is that the two bodies A and B are in contact. Then if body A exerts a force on body B, then body B exerts a force that is equal and acts in the opposite direction. So like A has got its weight, so because of its mass, its weight is a force acting downwards. Then B has a reactionary force that is equal and acts upwards. Okay, and that is something that we need to then think about for part B in this example. However, let's get into the example, do A first, and then we'll talk about B. So we've got a light scale pan. So this is just basically like a scale for holding some masses. Okay, you hang it by a string. It's attached to a vertical, light, inextendable string. So we know what that means. Tension is consistent right throughout the string, and we don't worry about the mass of the string. Carries two masses A and B. The masses are 800 for A and 1200 for B. A rests on top of B as shown. Scale pan is raised vertically upwards using the string with acceleration 0.5 meters per second. So for part A, you know, I'm going to deal with this as a whole system. So going down, we've got 800 and 1200 grams. So that's 2000 grams or 2 kilograms. So 2G going down. Upwards is T for tension. And it is accelerating at 0.5. So we've got to find the tension in the rope, in the string. So T minus 2G. So this is F equals MA. equals 2 times a half. So T is 20.6 newtons. Now, B part 1, we want to find the force exerted on B by A. So for that, sorry, just had to cough, we're going to resolve vertically. So think of A, and A has a downward force of 0.8 kilograms, isn't it? So 0.8 G newtons, and then a reaction like this, and acceleration of 0.5. Now, what I'm going to do here is, rather than find the force exerted on B by A, find the force exerted on A by B, and then using Newton's third law, it will be the same. So in this case, using F equals ma, we have R minus 0.8 G is equal to 0.8 times 0.5. So R is 8.24 newtons. So that is the force experienced by A from B. Therefore, the force on B by A is also 8.24 newtons. Okay, so just to recap this force that is the reaction force going up, that is the force experienced by A from B, and it's got to be equal to the force experienced by B from A. Okay, so that is how we go about solving that one. Now, part 2, the scale pan. So the force exerted on B by the scale pan. Now, this is a little bit more challenging. Well, not so much challenging, but challenging to think about. So we've got this scenario here where we know that tension, and then we've got this scale pan, and then this is, let's call this S. Sorry, S being inside, because what we're doing is finding the force exerted on the scale pan by B. Okay, so this again, now using F equals ma, would be T minus S. Now the mass of the scale pan is 0 because it's light. Therefore T equals S, or S equals T, which is, what was T? 20.6. So S equals 20.6 newtons. So force on B by scale pan is 20.6 newtons. I just noticed what I've written here. Force on by force on B by A. Okay, so that is this second example, and I think you'll find that thinking through what's happening is the hardest bit, getting your diagram right. Once you've got your diagram, like here, here, and here, it's relatively straightforward. You know, we're just using F equals ma, and we're dealing with those, you know, resultant forces. So that's the easy part. The hardest part is getting your diagram of what's happening right. Okay, and I cannot stress enough in mechanics, draw a diagram. every question. It's good practice to get into that practice of drawing a diagram for every question. So even if it's easy, draw a diagram. Okay, you'll get you into good habits so that when you get a question in the exam, you draw a diagram, you know exactly what's happening. You also make it easier for the examiner to follow through what you're doing. Okay, and potentially award you additional method marks where you might get the question wrong. So I can't stress that enough. Draw diagrams for your questions in mechanics. Now it's the point of the video where I remind you to hit that subscribe button, hit the like button if you found it useful so far, and if you're willing and able to help me out financially, hit that join button. Otherwise, let's look at the questions. So I've got 4 questions for you today, all past exam questions. So, pause the video a few times. So pause the video now. Okay, so that's questions 1 and 2 done. Pause the video now to have a go at question 3. Hopefully you're done with number 3. And pause the video now to have a go at question 4. Okay, hopefully you're done with all 4 questions. Stick around for the answers. So, question 1. We've got 2 particles A and B of masses 10 and 5 connected by a light inextendable string. Particle B hangs directly below particle A. Okay, so we've got 2 particles hanging like this, a string between them, so that is the tension there. Particle A and particle B. A force of 180 newtons acts upwards from A, causing the particles to accelerate. Find the magnitude of acceleration and the tension in the string. So for the first part, for part A, I'm going to deal with these as a single particle. So this is going to be a particle of 15 kilograms. So that's a 15 G newtons going downwards, 180 newtons going upwards, and we are accelerating upwards. So F equals ma. 180 minus 15G equals 15A. So that gives me 33. Divide by 15, and A is 2.2 meters per second squared. Now, part B, find the tension. So I'm going to consider this time B. So I'm going to resolve vertically. So that means I got T minus, and what was B? B was 5. So T minus 5G equals 5 times 2.2. So T equals 60 newtons. And, it would be the same had I done it the other way. If I, for example, did it with A, then I've got 180 minus T equals 10 times 2.2. Okay, and 10 times 2.2 is 22. 180 minus 22 Sorry, that's wrong. 180 minus t minus 10g equals 10 times 2.2. So 180 minus 10g is 82 minus 22, so t equals 60 newtons. So exactly the same, but a little bit more complicated when taking A, much easier to take B in this case. Okay, similar question to number 1, okay, but we're given the acceleration and we need to find one of the masses this time. So two particles, A and B, 6 and M, connected by a light inextendable string. So, you know, we've got this at 118 newtons to particle A, which is 6 kilograms. And then we've got the tension in the rope. This is to the mass of m kg, and obviously down here would be that overall weight. Okay, and we are accelerating at 2 meters per second going upwards. And we've got to find the mass of particle B. So at the moment, we don't know the tension in the rope, but what we do know, we know the acceleration. So we're going to do the whole system. Okay, and we're going to resolve vertically. Now, if I'm doing the whole system, and you know, I'm going to draw this out again, but you don't need to draw it. But that's 6 plus m in there. 118 newtons that way, 6 plus mg newtons down, and the acceleration is 2. So F equals ma, and we've got 118 minus 6 plus m in brackets times g equals 6 plus m times 2. Okay, so what I need to do is just now sort this out. So 118 minus 6g. This is going to give me 59.2 minus mg equals 12 plus 2m. So 59.2 minus 12 is going to be 47.2. And then this is 2m plus mg. So 9.8 plus 2 is going to be 11.8 m. So I've got 47.2 divided by 11.8, and m is 4. So that's 4 kilograms. Okay, so hopefully you can see, you know, it is still quite a straightforward question. Just got to think it through. Now, find the tension in the rope. So again, I could do it from A or from B. I'll do it from A this time. And I'm just doing it from A because say I made a mistake with finding the mass of B, then this should still be correct from A. So F equals ma, so I've got 118 minus t minus 6g equals 6 times 2. So 118 minus 6 times 9.8 gives me that 59.2 minus t equals 12. So taking t to the other side, 59.2 minus 12, we get 47.2 newtons, a figure we're already familiar with. Okay, so it's probably easier to use B to find the tension in the rope, in the string, but I used A that way because we didn't have to use our answer for part A then to solve part B, if you will. Therefore, just, ensuring that I have every chance of getting the correct answer. Right, let's have a look at number 3. So I've got a train engine of mass 6,400 kilograms. That's not just the engine, it's the front of the train that contains the engine. And it's pulling a carriage of 1,600 along a 6 straight horizontal railway track. So let's draw that out. So we've got this front one of 6,400 kilograms, and it is pulling a carriage of 1,600 kilograms. So the tension's the same throughout. Okay, now we've got, let's have a look. The shunt is light, yeah. Right, constant driving force of 12,000 newtons. So this one is 12,000 newtons. Obviously we have our weights here and our reactional forces there. That's the engine and that's the carriage. Okay, and obviously 64G and 1,600G, but we're not worried about those. So what else have we got? Oh, there's resistance forces. So the engine and the carriage are modelled as constant resistance forces of magnitude R and 2,000 newtons respectively. So I'll put this on in red. So that has R newtons and this one has 2,000 newtons there for the resistance forces. Acceleration is 0.5 meters per second squared. So we're going to find the value of R and then basically find the tension in the shunt. So finding the value of R first of all. Because we don't know the tension either, we can't deal with it as a separate thing. So we've got to look at the whole system and resolve horizontally. So F equals MA. Now going forwards is 12,000 newtons. And going against it is R newtons and 2,000 newtons. Now the total mass is 6,400 plus 1,600 or 8,000 and the acceleration is 0.5. Okay, so what I've done is I've assumed this as 1 unit. So 1 unit of 8,000 and the resistance forces is 2,000 plus R and the driving force is 12,000. Okay, don't know why I put the newtons in there. So we've got 12,000 minus 2,000 is 10,000 minus R equals 4,000. So R is 6,000 newtons. Now we've got to find the tension in the shunt. So let me just move that up, give me some room. So for B, let's look at the carriage. And we're resolving horizontally. So pulling it forward will be the tension. Going against it then will be the 2000 newtons. The mass is 1600 and the acceleration is 0.5. So T is equal to 800 plus the 2000, so 2800 newtons, which is what we had to show. Okay, very easy question, this one. Very easy, but it becomes easy when you draw the diagram out. Okay, much easier when you draw the diagram out, and it's easier to find the tension just by looking at the trailer or the carriage in this case, because you've got less forces to deal with. If you look at this one, we've got this, the tension and the resistance to deal with. Okay, and the resistance was a value we found, and we can't guarantee that's right, so we'd rather not use that value if we can avoid it in further calculations. Okay, so that's question 3. Let's look at number 4. Okay, so the first part of 4 is a car of mass 900 kilograms pulls a trailer of mass 300 kilograms, as if you see a car weighing 900 kilograms in today's world, along a straight horizontal road using a light tow bar which is parallel to the road. The horizontal resistances to motion of the car and the trailer have magnitudes of 200 and 100 respectively, and a driving force of 2000. Right, so let's draw out what's happening here. So here is my car, 900 kilograms. It has a force of 1200 newtons. Then I have a tow bar, which is going to have tension in it. Pulling a trailer of 300 kilograms. Okay, and I don't really need to put these in, but I will go ahead and put them in for you guys. But those are going to be unaffected in the question. Now we have resistances of magnitude 200 newtons and 100 newtons respectively. Right, so show that the acceleration of the car and trailer is 0.75. So for A, we're going to look at the whole system, and we are resolving horizontally. So F equals MA. So the force is 1200 minus 200 minus 100. The total mass is 1200 kilograms times by A. So 1200 minus 300 will be 900. Divide by 1200 and we get 3/4 or 0.75 meters per second. So there we have shown that A is 0.75. Now B, we need to find the tension in the tow bar. So let us look at the trailer and resolving horizontally. So again, we're looking at F equals MA. The forward force will be T minus 100. The mass is 300 and the acceleration is 0.75. Just move that up a little bit. So that is going to be T minus 100 equals 225. T equals 325 newtons. Now let's look at the second part of question 4. So the car's moving along the road when the driver sees a set of traffic lights have turned red. He reduces the force produced by the engine to 0. Okay, so no driving force anymore, and applies the brakes. The brakes produce a force on the car of magnitude F newtons, and the car and trailer decelerate. Okay, so we've got a slightly different scenario happening now. Given that the resistances to motion are unchanged and that the magnitude of thrust in the tow bar is 100 newtons, find the value of F. So we've got the car, which is 900 kg. We've got now joined to the trailer, which is 300 kg. This tension, okay, so the thrust in the tow bar is 100 newtons. So it's just calling it thrust instead of tension because it's going in the other direction. Okay, but let's look at the resistance forces. This one was 200 newtons and this one was 100 newtons. Okay, so all our forces now are acting to the left. Oh, and we've got a force of F, haven't we, which is the brakes being applied, which is also acting to the left. So 200 plus F acting in that direction. And we've got to find the value of F. So now in this case, it makes sense to take this way as positive. So this is the direction of the acceleration. Okay, so I'm going to take that. Now let's look at the trailer first. Because if we deal with the whole system, it takes out that tension, that thrust in the trailer. And we need that, don't we? Because if we look at the trailer using F equals ma, we've got a forward thrust of 100 minus a rear of 100. No, it's going to be plus because the thrust is pushing it back this way and it's got the resistance forces because currently it's moving to the right, so the thrust is pushing it to the left. And it's going to be 300 times A. So A is 200 divided by 300, or 2/3 meters per second squared. So that gives me the acceleration. Now, if I look at the car, in fact, what I will do is not look at the car, I'll look at the whole system. So for the car, if I just go back to this one with the thrust, the reason you know it has to be positive and not negative is because obviously there's not going to be zero acceleration. So in this case, it kind of is obvious, but you do have to be careful with that the thrust is pushing against it, not pulling it, because you've got to think about what's happening in the system. Now, for the whole system, we've got F equals ma. Now we've got 100 plus 200 plus F, and that's 1200 times 2/3. So it's 800, and that's 300 plus F. So F is 500 newtons. And that works just because all these forces are going left. My positive is left, my acceleration is left. Okay, so that is what I'm doing here. So hopefully you were able to follow this. I do understand this bit here is the bit that is probably the most confusing on this system, because we're talking about thrust rather than tension. Okay, and it's just really about the direction of that force is, kind of happening. We know that actually, in terms of decelerating it or accelerating this time, this arrow is actually pointing this way towards the 300, towards the trailer. So hopefully that makes sense. You do have to think about it logically, what's happening, to help you solve these problems sometimes. But hopefully I've made sense and you understood this problem and you got it right. Anyway, so that's the end of today's video. The next video we'll move on to some pulleys. So I think it's the first time looking at pulleys, but yeah, we'll move on to pulleys in the next video. So see you next time.